So welcome back to part 4 of our discussion of internal forces. In this particular section, we're going to be talking about beams, and we're going to decide to do this one a little bit differently than I've done some of the previous videos, and that what we're going to do is we're going to work on drawing shear and moment diagrams using that shortcut method that we outlined in the last using area-based approaches of the shear diagram and kind of building our progression. So what I want to do is kind of set up the framework for each of these problems and then work them kind of as we go. That way you can kind of see the constructions and the calculations that we're doing as we're trying to kind of work our way through. So I've got a series of 3 different examples that we'll look at, and we'll start off with something fairly simple and then we'll progressively get harder as we start to go through. All right, so in the first example, what we have happening here is a simply supported beam that has 3 point loads, a 20 kilonewton, a 30 kilonewton, and a 20 kilonewton force. Okay, and each of these are positioned such that they're 2 meters apart. All right, so these are loaded at the quarter points and at the midspan. All right, now if you recall from the last videos, we know that something special happens whenever there's a point load. Okay, and the point load causes an instantaneous jump in the shear value in the direction of the load. So if I come in at a certain value of shear to the left, as soon as I hit the 20 kilonewton point, the magnitude of my shear drops by 20 kilonewtons. Okay, and likewise, if I had an upward force like I do here at 35, I come in at a value and then I'll jump up 35. Okay, so we know something special happens at the locations of the point load. So that's what these dotted lines are going to indicate, all right? And so what I've done is I've also gone in and I've labeled the regions between the dotted lines as 1, 2, 3, and 4. So that will kind of get us set up for our approach here. All right, so now a couple of things to recall from last time. Okay, are our basic relationships that we're going to be taking advantage of in this. Okay, remember that our most important equation is this one, in which dm dx, okay, or the slope of the moment diagram, corresponds to the value of shear at the same location. All right, and in our last video we showed how we could kind of manipulate that equation to show that the change in moment between 2 points is equal to the area under the shear diagram between those same 2 points. All right, so here we go. Okay, so the first thing I'm going to do is I'm going to set up my framework that looks something kind of like this. Okay, and so the progression of the drawings is always done such that typically they're oriented in a vertical fashion. I'm going to take a beam and with my loading as the topmost picture, okay, and then I'm going to draw everything and align it vertically below that. All right, so the first drawing that I do is a shear diagram, and then the next one will be the moment diagram. I can't do moment unless I do the shear first. Okay, now if you remember, we talked about the order of polynomials on this, and so whatever n value I have for a given region or a given load up here, it increases by 1 as I start to come down, and I'll show you what I mean by that in case you've forgotten from the last video. All right, so here we go. Okay, so the basics is that we know that if I'm not on the beam, clearly I'm going to start out at a 0 value. Okay, and so I'm going to use the shear diagram. I'm going to look back up to the load diagram at every point. Okay, now each of these vertical lines that I have indicates that something's got to happen to my beam, okay, or to the shear values on that beam at those locations. Okay, and so as we've talked about with the point loads, I can come in and if I'm at 0 here, I'm going to move right on across, and as soon as I hit this line, something happens. I know because that's why the line's there. All right, and so I'm at 0 here. This 35 is an arrow that represents the reaction at the left support is going to push me up to a plus 35 here. Okay, and then I look and I say, okay, let's go look at the next critical point, if you will, or the next line that I have. And I'm going to ask myself, is there anything in between this point and this point that causes my shear to change? And the only thing that causes shear to change is load. And the only thing that causes shear to change within a region of a beam would be a distributed load, okay? And obviously up here I don't have a distributed load. So this guy basically stays the same coming all the way across, okay? And so that will get me those values there. So we can just kind of draw this guy all the way up. So I'm going all the way up to the line, but not quite on it, okay? There was nothing that caused it to change, so I'm still sitting at plus 35 at that point, all right? Okay, now I step onto the critical line and I have this 20 kilonewton force that's acting down. So this number now decreases by 20. So now I'm sitting at plus 15, right? Because 35 minus 20, that's 15. Okay, so that gets me to this point. And then I go and I continue the process and I look and say, okay, well, is there anything between this critical point and the next one that's going to cause me to change my value of shear. The question I always ask myself is it higher, lower, or the same? Okay, it's higher if I have a load that's forcing it up, it's lower if I have a load forcing it down, and it's the same if there's nothing in between. And in this case, there's nothing in between, right? So just like the last region, this guy kind of marches on across. Okay, so I can do this, and so I'm still sitting at plus 15. Now, as you might imagine, now I hit, pull this down a little bit, this point load of 30, and so I'm at plus 15. So if I'm at plus 15 and I subtract off 30 because it's down, I now go down to minus 15. This point now crosses 0, and it goes down to a minus 15 at that location there. Okay, and then likewise, same game, nothing causes it to change. Next point's at the same, okay, and it stays the same coming across. So that's this line. Okay, I'm still at minus 15. Okay, and then I hit the point load where this is at, and I drop by another 20. So I'm at minus 15, and I'm going to subtract the 20. I end up down at minus 35. And so this comes down to minus 35, and then nothing causes it to change as I go across, and so I hit this point at minus 35. Okay, now we're not done there, and this is where shear moment diagrams are pretty cool in that I can always check if what I've done is correct, assuming that the support reactions are right. Okay, I take my last point and I do that last calculation. So a minus 35, I hit this critical point, but on that critical point is a positive 35 force. So minus 35 plus 35 all equals 0. We check out. Okay, I hit here and then I step off the beam and I'm now at 0. All right, so what I'm going to do is now I'm going to add in positive and negative indicators because that will help me in drawing the moment. I'll draw this, and then I like to shade it just because it's kind of fun to color stuff once in a while. Okay, but also so that I can actually see the regions and the shapes a little bit more clearly on what I draw. So that's the shear diagram for this particular beam. All right, now we're going to slide this up. We're going to do the moment diagram. We're going to kind of play the same game. I'm going to start out at 0. Okay, and so my value at 0. Okay, and there's nothing that causes an instantaneous jump on the moment on this picture, right? The only thing that will cause that is if I were to have a concentrated moment, and I'll show you those in some of the later examples. All right, so where that point load of 35 caused a jump in the shear, it doesn't do that on the moment diagram. It's only on the shear. Now, basically, I can go in and I can just ignore that and do everything off of this picture unless there were concentrated moments up above. Everything comes off the shear on this because of that relationship that we showed you here. All right. Okay, so all we're going to do is we're going to go and we're going to ask ourselves, okay, I'm at 0. Is the point over on this line going to be higher, lower, or the same as that point? And the answer is it's got to be higher because that's a positive area, right? And because remember, we're going to calculate the area of this, okay, and that's going to cause me to increase because it's positive. So my next point is up here somewhere, okay? And then the amount that it goes up, so if I go delta M1, in this case, is going to be the area between those 2 points. So I'm going to take this 35 kips, and I'm going to multiply that by 2 meters. And so the amount that we go up is a plus 70 kilonewton meters, if you look at it there. All right, now we have the 2 points, but what does it do in between? Okay, so this is where we have to kind of start looking at the shape or the order of the function. We know that if we start playing with the polynomials like we did over here, that this is an n equals 0 function. All right, it's constant. Okay, and that's the definition of it using this x to the n power. Okay, so then if this is n equals 0, then this guy must be n equals 1. All right, and we know that an n equals 1 function is a linear function. Okay, it's either increasing or decreasing, but we've already said this one's increasing. So I'm going to lay this guy in something that kind of looks like that. Okay, now and the amount that he goes up then is that m2 is going to be equal to m1 plus the change from 1 to 2. If I look at that, and so this is going to be 0 plus 70. We're now at a positive 70 on that. All right, super easy, super easy. So this guy is a plus 70 here. Okay, now we go and do the same thing on the next region. We ask ourselves, is the next point higher, lower, or the same as this point? And we go back and we look, and that's a positive value. So we know that the next point has to be something a little bit higher. Now, obviously, it's not as much higher as the last region because it's a lot smaller area. And so this comes up and does something kind of like this. All right, and so if we come and we do our calculations again, the change from M2 to 3 then is going to be equal to, we have a 15 kips. Okay, that's the value of the shear at that point, and we're going to multiply that by 2 meters also, and so we're going up a plus 30 kilonewton meters. I think I said kips, but it should be a kilonewton, right? Okay. And so then my M3 on this is going to be M2 plus the delta from M2 to M3 is going to end up being, I started out at 70, okay, and then plus a 30 gets me to 100, okay, and so this value right here is plus 100. And away we go. All right, okay. Now, if we look, what happens is the rest of this beam is fairly symmetric, right? So if I start out at 100, the region that is here is minus 15 times 2, so we're going to come back down the 30 that I had. Okay, and again, this was an n equals 1, this was an n equals 0, and that's the way these all are. The point loads make this a very simple diagram. N equals 0, n equals 1, n equals 1 are the regions that we're looking at. So everything's kind of a straight line segment on our moment diagram. So this comes down to here. Okay, that's a plus 70. And then the last piece, just to kind of check it, then is that my last region that might change for M3 to 4 on this. So 2, 3, 4. Get ourselves here. That was a minus 15 kips times 2 meters. Sorry, I keep sliding off the page on you there. That doesn't help at all. Okay, is a minus 30 kilonewton meters. All right, so M4 then is going to be M3 plus the change between 3 and 4. And so we're going to be, we were at 100. I'm subtracting 30. That puts me at positive 70. And then we go in and we do our change from 4 to 5. Then is going to be minus 35 times 2 meters. Okay, is a minus 70 kilonewton meters. And so then my M5 is going to be my M4 plus that change, or something kind of like that. And you can see how we can kind of start building our way through this. All right, and so now we're at plus a 70, and I add a negative 70 to that. That gets me to 0. Therefore, we check, and we're okay. So the last piece of it looks something kind of like that. So the moment diagram on this picture looks something like that. All right, and if you want, and again, I often do this because when you get to mechanics, you can actually do some other things with this moment diagram. Once you have it, you can find slopes, you can find deflections, all sorts of stuff like that. All right, but that's our basic shear moment diagram for this very simple case. Now, to kind of show you about the regions that we defined, the region 1, 2, 3, and 4 on the picture as we defined them here, 1 being between the first 2 points, 2 between the second, and so forth on there. Recognize that what we're drawing, if we go back to our generalized equations format, is basically a series of sketches that look something kind of like this. All right, so for region 1, that was a cut somewhere between those first 2 points. The reaction we had was 35 kilonewtons, okay, and for every cut at any point in between here, wherever the location is, I can denote that as the position variable x. This is the generalized coordinate. All right, and then we put our internal forces in our normal orientation for shear moment diagrams. To the right positive, counterclockwise positive, and then of course down positive for the shear. Okay, because I'm working everything from left to right. All right, and so that becomes the free body diagram of this guy. Okay, if I go to region 2, again, we're working from the left, 35 up. Now this 20 kilonewton force shows up, right, because for region 1, over here, we were 0 less than or equal to x less than 2 meters. For region 2, we are now at 2 meters less than or equal to x less than 4 meters. Okay, that this picture is only valid on these intervals. So these intervals become very, very important for us if we were to try to write the equations. Okay, but the tricks on this are that I know this position of the load is always 2. That load doesn't move relative to A, or to that left support, okay? And then I know that the length to my cut from my reference is a distance of x. So it's these little guys are the ones that start to matter, okay? And so that distance is x minus 2, all right? Piece of cake, all right? Do the same thing for the third one. Okay, now we pick up, we still have that first point load, but now I pick up the second. The limit is from 4 meters less than or equal to x less than 6. Okay, and so same thing, 35 kilonewtons up, it's a distance x over to here. Here are my coordinates, that doesn't change. All right, and then so the only thing we have to do is we have to come up with that quantity, and so that guy is going to be x minus 4. All right, and so we've got it. Okay, and then last but not least, same process. Okay, 35, now I got the 20, the 30, and the other 20. My cut is still, so we're out in that fourth region. Okay, and then this piece right here is going to be x minus 6. And our interval is from 6 meters less than or equal to x less than 8 meters. All right, and so that gets us through our first example. No major tricks, right? So hopefully that kind of illustrates what we can do to generate a shear and moment diagram for a fairly simple case. Right now, let's ramp it up a little bit. Okay, and so what we're going to do is, well, here, let me go back for 1 second. Okay, remember the whole point, or the whole issue that we were dealing with was moving from one line to the next. Well, the question that we have is, well, how do we know where to put lines? Okay, and so there's a small little checklist that we'll put in as we start to look at this. Okay, we knew from past experience that concentrated loads were one of the important ones. All right, because we knew that the shear diagram would jump at those locations. Okay, but there are several others that we want to also keep our eyes open. All right, and that's the nature of the next picture. All right, so we're going to locate critical points. Okay, the location of those dashed lines that we had on our example. All right, so there are 5 of them, 5 categories that show up. We're going to do a start and end of the member. Okay, I'm going to do all support locations. I'm going to do concentrated forces or moments, anywhere that I have a concentrated force or a concentrated moment. Okay, and then I can do the start and end of any distributed load. Okay, and then last but not least, and this one you have to wait to do until after your shear diagram is finished, and that's the location where V equals 0, because if you recall, because of dm dx equal to V, if I set that equal to 0, then this becomes the location of M max, or the min. All right, and that's a very important value for us, so that's why we always add this one and want to include him. But to start off with, you can't draw him because you don't know on those. All right, so let's try it. Okay, so what we've done is I've gone a little bit more basic. Okay, I have a simply supported beam, a point load of 60 pounds. Okay, get a couple dimensions on here. This should be 10 feet. Okay, and then I'm going to put 5 feet between here, and now we have a concentrated moment. So I'll show you what happens when those guys show up. Okay, all right, so if we go down our checklist, okay, the first one was the start and end of the member. So that's these 2 lines, this one and this one here. And basically, that's just the bounds of the graph. Okay, our support locations, okay, happen to be the same thing. So if this was number 1 and then number 2, all I'm doing is labeling these things. That's a 1 and that's a 2. Okay, if I pull this down a little bit, okay, the next one says any concentrated forces or moments, so I can have a line coming down here, and then I can have another one that comes down here. Okay, and so that becomes my number 3, and that becomes my number 3. Okay, and then the start and end of any distributed loads, there are no distributed loads, and then the last V equals 0, we don't know that one yet. Okay, now, you'll notice I've already worked out the support reactions for you. I have 100 pounds up and 500 pounds up. That was a 600 pound point load, and then this clockwise moment of 4,000 pound-feet that will show up. Okay, so the picture looks just like what we did. The shear diagram, we're going to play the same game. I'm going to start out at 0. Okay, I'm going to hit that first critical point. It goes up to plus 100. Okay, and then look at the next point and ask myself, is it higher, lower, or the same? There's no load up here, so this guy is the same. Okay, so that goes to plus 100. Okay, I then hit this point load, which drops me down to a minus 500. That's 100 minus 600 is minus 500, so that's this line. Okay, and then I ask myself, go to the next critical point, higher, lower, or the same. There's no load in the middle region, so it's basically the same value coming across. Okay, now I'm sitting at this critical point. Okay, now this critical point got added in because of the moment. All right, moments do not affect the shear diagram, so it's almost like he's not even there. Okay, he will affect the moment diagram when we get down there. Okay, so our next point then, so we just basically say nothing changes. So I came in at minus 500, I go out at minus 500. Okay, and then we go and we play the process all the way over and we ask, okay, next point, higher, lower, the same. There's no load in that region. So basically it just continues on trucking across. Okay, and so now I'm at minus 500. Okay, and I hit that point load. This is the check that you want to make sure you do. So I go minus 500 plus the 500. That brings me back up to 0, and then I step off. Okay, so we're good. That checked out. Okay, so let's call this as a positive value. Okay, this is a minus. Okay, and this is a minus as we start to look at that. All right, okay, so now let's go down and let's do the moment diagram fairly quickly. All right, okay, now we do need to do one thing before we do that, though. All right, let's go back up to our list and let's figure out. Okay, this v equals 0 is an important point. So where was our shear a 0 value in this? Well, it's 0 out at the ends, which we already have those captured, and it's also here. Okay, now for us, we already have a critical point there, so I don't need to add another one. Okay, but if for some reason this had been a 0 value over here, I would then add that line as a critical point, and then I would have to step through all of those because I got to be able to capture the maximum or the minimums on those. Okay. All right. So now we're going to start out for the moment diagram. I'm going to start out at 0. I'm going to go to the next critical line, ask myself higher, lower, or the same. Okay. Now, if you look, this was a positive shear area, right? So the area under this causes a positive change to the moment here. So my first point is going to come up to something that looks like this. All right. So if I call this as M0, so M0 we said was equal to 0, okay, and so the delta M from 0 to 1 then is going to be equal to the area under that curve, and so that's going to be plus 100 pounds, okay, multiplied by 10 feet, okay, is going to be equal to 1,000 pound-feet, okay, and so then M1 is going to be equal to M0 plus delta M01, and by now you see the game. This becomes a plus 1,000 pound-feet. Okay, that's all we're doing. Okay, so this guy is plus 1,000 there. All right, okay, now, again, we're going to play the orders. So n equals 0 because it's constant. So now this becomes n equals 1. We know that's linear, so I just basically connect the dots. Nothing fancy. And we've got that particular piece. Okay, so that's a positive. Okay, and I can shade this guy a little bit if I want to. And we're good to go. All right, now go to the next point over on this line and ask yourself, is it higher, lower, or the same? Okay, and the way that we tell is we look at the sign on this, and this is negative, so now it's lower. Okay, all right, now how much lower? Well, it's the area of that piece. Now I'm going to stop at this line because I got to take care of that concentrated moment, but the next point is going to end up dropping me down to something like this. Okay, and so the way that I know that then is that I can say the delta M from 1 to 2 is going to be equal to then minus 500 pounds, okay, multiplied by 5 feet is a minus 2,500 pound-feet. All right, so this point, so my M2 then is going to be plus 1,000 minus 2,500 is going to be a minus 1,500 pound-feet. All right, and so this value is minus 1,500 sitting right there. Okay, now again, n equals 0. This is an n equals 1. It's a straight line, and it comes through and it crosses and does something like that. All right, so we got a little bit of a plus guy happening there, and then the most of it is a negative happening there. All right. Okay, now for the issue that we have. At 3, okay, and you need to check this at every point that you come across. Is there a concentrated moment? All right, and so here's what we're going to do, and the way that we look at this and the way that we remember. I have a moment that is clockwise. Okay, well, if you remember our sign convention for moments, we said we're going to define this as our positive sign convention. Remember, positive moments make us happy, right? Okay, but that's what we called as a positive M. All right, because we're working this from left to right, the one that we're going to look at that sets the sign is the one on the left. All right, so left to right. So what's going to happen is that with this 4,000 that's on here, that's a clockwise, because that's clockwise, and that's our positive sign for these applied moments, these concentrated moment effects, is I'm going to come back and I'm going to say, all right, well, my change at this location is going to be minus 1,500 where I started, and then on that same line, I'm going to instantly jump back up. So this is like that concentrated moment. You know, remember what the shear did to the shear diagram, this point load. It caused an instant jump. Well, the concentrated moment causes a jump in the moment diagram. All right, so if I sit at minus 1,500, okay, and I add now 4,000, okay, that's going to put me at plus 2,500 on this one. All right, and so I can come up and do something that looks like that. And so now we're at plus 2,500. Okay, and that will get me to there. And then to close it out, over here, my delta M is going to be 500 pounds. as a negative value multiplied by 5 feet is a minus 2,500 pound-feet. That's the delta that comes off of this. So I'm at plus 2,500. I subtract minus 2,500. That brings me back to 0. So plus 2,500 minus 2,500, all equal to 0. That checks out. All right, and so that becomes what the diagram looks like. All right, and so we'll call that as a plus, and then we'll shade all of that. And so that's how you construct that one. All right, so now you see how to handle these concentrated moments. The one thing that we haven't talked in these first two examples is distributed loads, and there's one other issue that comes up with that. So we'll run through that one fairly quickly. By now you've kind of seen how all this is working, but that's all there is really to drawing these shear moment diagrams. You'll notice I didn't draw a free body diagram anywhere, and I didn't have to write generalized equations. I just kind of progressed my way through the areas and was able to build these pictures very, very quickly. Okay, and again, as a design engineer, this is one of the first steps that I have to go through in order to be able to do a beam design. Okay, all right, so let's try one that's a little bit more involved. Okay, and so we get something that looks like this. Now this beam is a cantilever beam. My supports, the first support is inset a little bit. I have a point load of 600 pounds. I have a counterclockwise moment on the end of the cantilever. I have a 3,000 pound-foot concentrated moment at this point, and then I have a distributed load that's happening all in between. Okay, and then of course I have 2,600 pounds up, and then I have a 1,000 pound reaction. I've given you all those. So all we're going to do is we're going to go locate our critical points. So the first critical point is here. Okay, the second one is going to be here. Okay, and generally I like to draw these pictures somewhat big, just to give myself a little bit of room. I haven't done the best job of that today, but that's all right. Okay, and then this is the one for the concentrated effects. Okay, as well as the start and end of the distributed loads. And then this would be the end of my beam. So that becomes the set of boundaries that we're going to need in order to draw the shear in the moment diagram. All right. Okay, all right, so let's do it. So the first picture that we draw is our shear. As I start to come through here, so there's a shear. We're going to start out at 0. Okay, now if you look, this is a negative load, this is a negative load, okay, because the loads are acting down for us. So we basically play the same game. We go to the next critical point. So this one actually has 3 critical regions. There's a 1, there's a 2, and there's a 3, because critical regions are defined by the critical points. They're the area in between. So if I were to do the generalized free body diagrams to get the equations, I would need 3 of them to fully define this beam. That's kind of the beauty of that checklist that I showed you. Okay, so what we're going to do is we're going to look at this and we're going to say, is the next point higher, lower, or the same? Well, the load was negative. So clearly, you know, unlike all of the other cases where there was never any load out in the middle of this thing, now there is. All right, and so what we do is we basically say, I'm going to start out at 0. The next point is lower on this. Okay, now this was an n equals 0 load. Again, we're playing f equals x to the n on this. So this means that this guy better be an n equals 1. Okay, so it's a linear function, whatever it is. So I'm going to go ahead and draw that, and then we'll figure out how much it went down. Okay, well, just like we did before, the amount that it goes down is equal to the area between the 2 points. All right, so now we have a delta V on this that's going to be equal to the area under the load diagram. Okay, so that's going to be a minus 200 PLF, and we're going to multiply that by... All right, sorry about that. I realized I've left off the dimensions of the beam. Now, for shear, it doesn't really matter. Well, in this case it does because I have a distributed load, but it's 5 feet, 10 feet, and 5 feet. For those portions of it. So if we go back and calculate the change in shear, this is minus 200 PLF times 5 feet. Okay, that's going to be a minus 1,000 pounds. All right, so this guy is sitting here at minus 1,000. Okay, and so that becomes a minus. We'll need that. Okay, and we know that it's linear, so it's an n equals 1. Okay, and then I hit that critical point, and then on the shear diagram we look at the line. I do have a concentrated force, so this is going to bump me up to a plus 1,600. Okay, and then I go and I look at my next line, and my higher lower are the same, and it was a negative load, so again I'm lower again. Okay, well, how much lower? So if that was delta V1, let's call this as delta V2 for region 2. On this it's going to be minus 200 PLF multiplied by 10 feet should get me to a minus 2,000 pounds is the change. All right, so if I was at plus 1,600 and I go down by 200, this line's actually a little bit higher, so that should be a minus 400 that gets me to there. Okay, and again, this is n equals 0, which makes this n equals 1, so that's a linear line. And there we go, okay? But also at this point, you'll notice that I have this concentrated load, okay? So if I was at minus 400, minus 600 will put me down to minus 1,000. Okay, and so there's another jump happening on here, okay, because these point loads, they take precedent. You'll notice that the slope of this line was the same as the slope of this because the load was the same all the way across. But as soon as I hit this point down here, that point load of 2,600 pounds interrupted what I was doing and threw me instantly to the new value, okay? And then we can come in and we can look at the last piece. We can say, is there anything next point higher, lower, or the same? There's no load now. The distributed load has stopped. So this guy becomes just straight across and looks something kind of like that. So this is, there's no undefined, so this is actually the n equals 0 case. Okay, and so that's a positive. This is a negative. We'll shade it real quick for a good measure. And that will get us there. So that's what your shear diagram for this picture looks like. Okay, now notice it had nothing to do with the two applied moments that are on there. So we'll handle those when we come down and draw the next diagram. All right, so here's my M. Okay, and if we look, okay, so we start out at 0. I step onto that first critical point, which is the end graph, and that's where this 1,500 pound foot is happening. Now remember, we're looking at the left end of this thing, so this is actually a negative moment. So I started out at 0, I get thrown down to minus 1,500 instantly. Okay, and so that becomes my point that looks something like there. Okay? Okay, so then we come in and we say, relative to this point, is the next point higher, lower, or the same? It's a negative, so the next point is lower. Okay, this was n equals 1, so now we're at n equals 2. Okay, and if you'll recall, the way that we kind of start reasoning our way through all of this is that I have 2 points. Okay, and because it's n equals 2, there are 2 possibilities for what it could be. It could be either number 1 or number 2. Okay, and so we can go back and we can look at our relationship dm dx equal to v, that the slope of this curve corresponds to the values of the shear diagram. Okay, so if you look, my highest value, in fact, in this case, is a value of 0, which means that the slope at this point has to be horizontal at 0. Okay, and then the slope at this is my highest negative value, so it's fairly steep. So this guy is kind of doing this as an n equals 2. All right, and again, we're looking at the slopes or the tangent lines at the endpoints to help determine that. All right, so that's a minus. That will get us this piece. Okay, now I step onto this point, okay, and if you recall, there was a concentrated load. It doesn't do anything to the moment, so I just basically ignore this guy now. We're just back to looking at what happens up here in this mid-region. Now, we have a new problem that shows up here. Okay, and I'll jump down here and kind of draw you the issue. All right, we went from 2 points, one of which was plus 1,600, okay, and the other is minus 400, and it was a straight line that approximated the whole thing. Okay, if you recall, on our critical points, that means that there was a 0 that's here. Okay, because it went from positive to negative. I had to cross 0, which means I need to be able to drop in an extra critical point. That's the v equals 0 critical point coming in for us there. Okay, but the problem that I have is that I don't know where that is. Okay, so if I look at this, this is the way we're going to do it. We're going to say that the whole side of this thing is 10 feet. Okay, and if I just give myself some vertical lines to kind of work my way through this. Okay, all we have to do is come in and say, let's call this is x, and I can do proportions on these triangles such that 1,600 goes to x, okay, is going to be the same as 1,600 minus a minus 400 goes to 10. All right, and so what happens then is that I can solve this proportion here to find out that x is equal to 8 feet. Okay, and you can check the math on that, but I'm pretty sure that that's right. Okay, so that becomes 8 feet. So I know that the distance here to where that 0 is 8 feet. So the maximum bending moment in this guy is going to be 8 feet to the right of this support here. That will be over the location of my maximum on the moment. Okay, and I need that because I got to be able to define the bounds of the moment. So we're sitting then at this value when we did this for a moment diagram. Okay, that we know that it was a second order. I guess I kind of forgot to write the value. So let's do this real quick. So we have our delta M0 between M0 and 1. Okay, was going to be equal to then the area, which is 1/2 of my distance of 5 feet multiplied by 1,000, by a negative 1,000 pounds. And so the change in this is going to be equal to a minus 2,500 pound-feet. Okay, so if that's minus 2,500 is the change, I was at minus 1,500. This number is now minus 4,100. Okay, because it's minus 1,500 plus a minus, sorry, I misspoke. It should be minus 4,000. Okay, minus 1,500 plus a minus 2,500, okay, is a minus 4,000, gets me to that value. Okay, now the next point we go, is it higher, lower, or the same? Okay, well, I know it's higher, but I don't know whether it's going all the way positive or here, so let's just calculate that change between 1 and 2. Okay, and so this is where I'm going to use that 8 feet. Okay, the value of the shear was 1,600 here, so it's 1/2 of 1,600, okay, pounds multiplied by 8 feet on this, okay, should be a positive 6,400 pound-feet is the change from my current point. Okay, so if I am at minus 4,000 here, okay, and I add 6,400 to here, this one comes up and gets me to a positive 2,400 on that, okay? And again, minus 4,000 plus a positive 6,400 gets me to a positive 2,400 pound-feet. That's all I'm doing is writing that equation, okay? Now, what's the order? It's n equals 1 on this guy, which means this guy is an n equals 2. So now we're going to play the game. All right, well, I have this point and this one. The two possibilities are this and this, right? Okay, and so if I play the dm dx equals v game again, if I start to look at this, then we can kind of look at our values. Okay, so at this location, v was 0. So it's basically horizontal, and here's my most positive. So this guy is coming in and doing something kind of like that, okay? And it's an n equals 2 function. So we're minus here, and I'm positive here, okay? And I know that that's my max, because that was at the location of v equals to 0, okay? So finishing this thing out fairly quickly, okay, we know that this is 2 feet. I'm at minus 400. Okay, so if I'm at plus 2,400, then the area of this triangle is 1/2 of 2 times minus 400, or minus 400. So this guy comes back. The next point, if I play the higher, lower, or same game, is he's lower because it was negative, and he's lower by an amount. Kind of running out of room here. Okay, that the delta from m from 2 to 3 is going to be 1/2 times minus 400 times 2 feet on this is minus 400. So if I'm at positive 2,400, now I'm at positive 2,000. Okay, and same process. This is an n equals 2 curve because of the distributed load. Okay, and if we look at it, the slope at the left end is horizontal and it's mostly negative, so it's not real pronounced, but it does have a little bit of a curl that brings me back up to the negative, and then it drops off, something kind of like that. So that gets me to this one. Okay? Now, the last piece of this then is we go through and we say, all right, now I'm stepping onto this critical point, and if we go back and look, that was the location of this 3,000 pound-foot moment that's acting clockwise, or acting as clockwise. And again, we're looking off of the left end of this thing as our sign convention. So our positive sign convention said that was positive on the left end. All right, so if I look at that piece, we're now up as a clockwise moment. This is clockwise. So my value goes from plus 2,000 here, and it jumps up to plus 5,000 there. Okay, and so we can now add that line. That was an instant jump because of the moment. Okay, and then we can look at the last piece fairly quickly. I see that this is minus 1,000. We know that it was 5 feet. Okay, so the area of this is minus 5,000. All right, and I'm sitting at positive 5,000. So 5,000 minus this guy will bring me back to my 0 value, and then I step off. Okay, now n equals 0. That makes this guy an n equals 1. And so that becomes the moment diagram for this guy. Okay, so you can see there are a couple of tricks in dealing with this. And I know we've gone kind of long on this, but so I'll summarize fairly quickly on this. But that's my moment diagram. It's pretty wild, right? But by doing this, I can go in and I can figure out where am I designing for the maximum moment. Okay, I have a negative 4,000 here that might be a concern, but it's this 5,000 guy directly at that point load where that concentrated moment is that's the issue. And so I would design this beam for a positive 5,000. Okay, and if it's symmetric, then I don't need, in terms of loads and design, then this 4,000 would be covered by that. Sometimes you do need the lower negative, so it's good that I have both. Okay, but that becomes my value. Even though I thought this was a maximum, it wasn't the maximum overall. Okay, it was a maximum that corresponded to the 0, but my actual maximum then is outside of that range, and it occurs just to the right of that point. Okay, and so that's how I end up, and that's how I know it. Okay, so it's pretty straightforward. It's not too bad. I hope this has made some sense. There are a couple of tricks again. Okay, the biggest trick on these is anytime you have a distributed load and it crosses 0 at this extra point, you've got to be able to figure out what is that dimension right there. Okay, and so once I have it, then I can build the rest, and that allows me to get the max. That's the only way to get the max, is to know that dimension. Okay, so you have to be able to find it, and you have to be able to do proportions. Now, if this is some other function that's, it's a curve of n equals 2, it gets a little bit more pronounced, but for most undergraduate statics classes, and even in practice, most of the time, this guy is linear. I can do it by proportions, and we're good to go. Okay, otherwise you'll have to apply a little bit of algebra and some geometry to figure out the rest of it, but it's not a big deal. So, all right, well, I hope this has clarified the methodology. I apologize for being all over the place, and I apologize for the length of the video, but, engineering takes time. So with that, we'll let it go. As always, if you leave a comment, if there's anything we can do to make the videos better, please be sure to leave a comment down below. Okay, please subscribe, and we'll keep putting out videos to kind of help out with some of these basic engineering classes as we go along. So anyway, have a great evening, and we will talk to you all next time. Thank you. Bye-bye.